Imagine a world where you can move the cursor on a screen just by thinking about it, or that you could play video games with only your thoughts, or that you could download information directly to your brain from the internet. You'll probably think that all of these is far away in the future and belongs to science fiction. But what if I told you that we are already living in this world? We communicate with machines through various interfaces that we have perfected throughout the history. From punch cards of the first computers to the touchscreen that we all take for granted today, we were quite inventive on how to transform our computers to a literal extension of ourselves. The brain-computer interface, or BCI, continues down this path of innovation and does something that has never been done before. It allows a real-time, bidirectional pathway between the brain and the outside world, eliminating the need for any intermediates, even your own hands. This technology is first used as an interesting alternative for people struck by neuromuscular disorders and amputees. It enables them to use neuroprosthetics, speller programs, or other amazing devices that could be employed for restoration or rehabilitation. Normally, when a person wants to grasp an object, the brain sends a command signal via the nervous system. The message travels through the nerve fibers in the spinal cord all the way to the muscle, which contracts upon receiving the command. What makes BCI interesting is that it bypasses the brain's neuromuscular system. Instead, the user's intent is directly transmitted by an interface that records the brain activity and translates it into useful messages that commands an application. Nerve impulses are extremely slow compared to the speed of electricity. While a message travels at 100 meters per second through the nervous system, it can theoretically travel as fast as 300 million meters per second with a brain-computer interface, which makes it the ultimate form of communication between a human and a machine. Research first started at the University of California in the 1970s. Computer scientist Jacques Vidal was the one who coined the term brain-computer interface. Later in 1998, Philip Kennedy's team established the first fully developed BCI system. He implanted a neurotrophic electrode into a brain of a patient with locked-in syndrome. Thanks to the implant, the patient was able to communicate by moving a mouse cursor on a computer screen. There are two main types of BCI, invasive versus non-invasive. Both have advantages over the other. Non-invasive BCI is mainly done by recording EEG data with electrodes. Electroencephalography is the recording of brain waves produced by populations of neurons located in cortical areas, the outermost layer of the brain. Captured signal is then amplified, digitally converted, and processed by a computer in order to predict an individual's mental states. It is possible to categorize EEG signals according to frequency, so different frequencies correspond to different mental states. For example, alpha waves correspond to awake at rest. In the context of the BCI, it is particularly useful to take advantage of the phenomenon called event-related potential, which is a psychophysiological response of neurons to external stimuli. We can, for example, cite the famous P300 waves widely used in BCI paradigms. Invasive BCI, on the other hand, the one Neuralink is based on, has a much better resolution naturally, as it forms a direct physical line with the neurons. The drawback is that you have to place electrodes surgically, which creates a myriad of problems to tackle with, such as bioincompatibility or infections that might arise during the operation. BCI is a multidisciplinary domain, especially signal processing, which is an important part of this job. For this, machine learning methods and neural networks are usually employed. If you're an engineer in an unrelated field, but with the correct know-how, you might start working on a BCI project relatively easily. Despite many recent advances, we can't see more prevalent use of BCI in our daily lives yet, because there are some technical hurdles to solve first. Calibration is a big issue, for example. It takes a patient weeks, even months to train for a neuroprosthetic arm specifically made for them. A lot of teams around the world are working on this problem as of now, relying on advanced machine learning techniques to do so. Finally, there is a strong open source community built around the BCI field, with various projects such as OpenBCI, using common programming languages such as Python or MATLAB, devices under $1,000, and companies that dispense built-in packages like Emotive and NeuroSky. With the advent of more compact systems for brain activity measurement, people quickly understood the true potential of BCI for healthy people, enhancing human function. The concept of neurofeedback is a prime example. By monitoring brainwaves in real time and feeding it back to the user, we can expect them to control to some extent the brain activity and achieve cognitive improvements such as memory, attention, processing speed, or executive functions. By taking control of your own hidden variables, you can stay more focused and become better performing at your task. BrainNet is a brain-to-brain interface used for collaborative problem solving. The interface combines EEG to record one user's brain signals and transcranial magnetic stimulation to deliver information to another user's brain. All of these non-invasively, of course. During the experiments, a group of 3 people played a Tetris-like game. They were able to communicate without saying any word and effectively share information to whether rotate a block or not. This amazing technology could pave the way to a future where people cooperatively solve problems by wiring themselves to a social network of connected brains. It can be useful in critical jobs that demands constant awareness to share cognitive load between colleagues, reducing fatigue and human error. As with anything, this technology could also have unintended uses that we can't predict. It is one step further to apply what we learned from video gaming with BCI to controlling military drones with thoughts, greatly upsetting the balance of forces in the world. Reading directly the brain activity of an individual also poses privacy concerns. In conclusion, this technology holds the key to revolutionize our way of living and open new horizons and could balance the advent of artificial intelligence by enabling human brains to keep in pace. With Moore's law, which refers to the observation that computers' capacities are doubling every couple years, we can predict that machines with human-level intelligence may arise as soon as 2029. Brain-computer interface does not propose to surpass AI, but instead merge with them, which may be our only hope to stay human in near future. It is thought that a hybrid system of AI and human agents collaborating could even be better performing than both of them, complementing on each other's weaknesses. In any case, we shall not leave careful reflection on these issues for later, but try to foresee all possible futures and guide ourselves towards the best outcome for our species. No matter what we do, we should not make any concessions from our humanity, meaning our values rather than our fragile bodies.